Okay, in this video, we are going to do the rest of the core atoms topics besides nuclear. So we're going to do all of these questions, the multiple choice questions for bonding and periodic trends. And then there's a substantial amount of part two questions on this. So that'll give us a good launching off point for that. So again, this will get you a whopping 13 points. In this exam, it was 20 points worth of material between both of these videos. So let's keep our fingers crossed that this exam looks like January 2025. Let's head over to the Regents and just start knocking off questions. So at the topic review sheet, which I'm going to post in the description for every video, has the links to get to the state website, but you can also just Google New York State Regents and it will pop up. So for this section, we're going to go back and start at number 6. And that is because I have this topic classified as bonding. And if I'm not mistaken, when I go over this section, um, I do it in the beginning of bonding. And I go over sort of the basics of what atoms do when they bond. And one of the most interesting phenomena is something called allotropes. And they love to just throw like one allotrope question at you every year. The word allotrope, let me spell it for you. If you remember when we did the lab, Meet the Elements, and we had all the elements out in the lab, and you guys kind of walked around and looked at them, and some of them you could touch them. When you got to the bench where carbon was, there was diamonds and there was pencil lead. So carbon has different forms. It's pure carbon, but depending on what the carbon atoms were exposed to when they crystallized into a form that we actually pulled out of the ground, um, that can produce different molecular structures. In other words, these nonmetals can bond to make different types of structures. And those are different forms of the actual element. So they have different molecular structures and they will actually have different properties. So think about what we call the lead in your pencil is not lead, not lead like PB, the metal off the periodic table. That would be insane because lead's poisonous. It's never been lead. That's the craziest part. Um, it's graphite, and graphite is a form of carbon. Now consider a diamond. How different those two things are. They are both made of pure carbon. What's making them different is their molecular structure. And since their structure is different, it's giving them different properties. In other words, the qualities that you associate with those things. One is very soft and you can rub it and it makes a mark. The other one is one of the hardest substances on Earth, um, is diamonds. It's very high on the most hardness scale, and it's usually a very clear crystal structure. Although there's depends on the quality of the diamond. So there's two other elements that they like to bring up on here, and I put them in my slideshow, so I'm going to link that slideshow to this. The other two are phosphorus and oxygen. And each of these have also a different elemental form. Phosphorus has two other elemental forms. It comes in sort of three flavors, white, black, and red. Almost all of them are pretty dangerous, the most dangerous being white phosphorus. And oxygen comes in two different flavors. It comes in O2, which is great, breathe. You breathe oxygen, it's important, it's part of your body's ability to chemically break down glucose. When you do cellular respiration to break down stored glucose and make ATP so you can use energy, you use oxygen at the end of that process. It's not actually necessary for the process itself. It's a last step, but we won't get into it. Ozone, this is one more oxygen, very unstable, dangerous compound. Ozone, way, way up in the stratosphere, is a great thing. The ozone layer protects us from UV radiation coming from the sun. Ozone down here, where we're breathing it, made by air pollution, is actually really dangerous. It's a very bad respiratory irritant, and it can cause respiratory problems even for people who don't have like asthma. But if you already have asthma or something like that, one of the air quality alerts that you will get is that the ozone levels are high. We are not meant to breathe in ozone. It's a much less stable form of oxygen. It's actually very, very reactive, and for that reason, it can damage your lung tissue. Whereas just two oxygen together is a lot more stable. So, what is causing this is the difference in molecular structures. And so, I will link the slideshow to this in the description to help you review that. So your answer is they have different structures and they have different properties. So when they bring it up as oxygen, it's a little harder to uh, hold on to in your head. But if you can keep that list in your head, phosphorus, oxygen, carbon, carbon tends to be the easiest one to remember because of this thing with graphite and diamonds. And you can kind of hold on to that memory of graphite is this slippery, soft elemental form of carbon, and diamonds are totally different than that. So this is actually allotropes. They may not use the word allotropes, but that's what number 6 is about. And it has to do with bonding and structure. So that's why it's grouped with these questions. All right, so let's head over to our next question is question number 8. What type of bonding is present in a sample of zinc? The fact that it's at standard temperature and pressure is not all that important, but all metals are solids at standard temperature and pressure. And if you're dealing with a pure sample of a metal or a metal alloy, which is a mixture of metals only, they're not bonding with nonmetals, then you are dealing with metallic bonding. So I think metallic bonding is in this exact same slideshow. So when I link it, I think you're going to see metallic bonding is there also. So if it's a metal, if it's pure metal, iron, copper, gold, zinc, I don't care what metal they give you, it's metallic bonding. If they ask you if it's metallic bonding, pick the metal off the list. Please don't make up anything else. I'm not really sure why you guys get turned around on this, but it's a little frustrating. All right, now we get into polar and nonpolar molecules. Um, this is a very difficult topic to review because it would take me a really long time and it's not an easy topic. Again, I can link slideshows, but I don't think you have time to go over this. So my advice to you at this point in the game is to memorize two important things. One is what is a rough definition of polar and nonpolar, and the other one is a list. You should memorize a list of which molecules that are they're going to bring up that are polar and nonpolar. Okay, so I believe those lists are actually in my slideshows. So I'm going to link the slideshow rather than go over the whole list. But you should know that water is a polar molecule. It is what gives water most of its really important properties. But the other two here that are polar are ammonia. That's a common name. Nitrogen trihydrate is the real name. And hydrogen chloride, otherwise known as hydrochloric acid if it's aqueous. So the only one here that's non-polar is methane. Methane is an important non-polar molecule. It's also your smallest organic hydrocarbon. So these are molecules I've said since the beginning of the year. You see them all the time. You should know who they are. Okay, so people like methane, water, ammonia, you should know who they are. Hydrogen's bonded with people from group 17. You should know who they are. So I'm going to link that slideshow because I think that I have these lists already written out for you. If not, I'll make sure I add it to the slideshow before I attach it. So nonpolar is methane. And the definition you need to memorize. If it's a molecule, there's a difference between a polar bond and a polar molecule. A polar molecule has an uneven or asymmetrical distribution of charge. A nonpolar molecule has a symmetrical or even distribution of charge. Okay, so that's kind of all you have to memorize. Now, if I were to pull up for you, and I can do it pretty quickly because I have all this stuff on my tabs all the time. If I look at the core curriculum, remember I brought up the core curriculum because it's the master list of everything you need to know. And then head down to page 30. I'm going to go to chemical bonding. See chemical bonding? Okay. Uh, this is the list of everything you're supposed to know. There it is. Molecular polarity can be determined by the shape of the molecule and the distribution of charge. If you don't understand what that phrase means, you really got to sit with it. Distribution of charge. What's distribution mean? How is the charge spread around? Like uh, if I were distributing cupcakes in class, did I distribute them fairly and evenly to everybody? Or did I give like five people all the cupcakes? That would be an uneven distribution of cupcakes, right? It would not be fair. It would be a very polar distribution of cupcakes. All right, and then it talks very specifically. It uses all the language they're going to use in the question. Okay, and they even give you, oh my gosh, they give you the list. This is why I love giving you this document. They give you the list, you guys. They gave you the list of symmetrical molecules they're going to bring up in questions. Nonpolar molecules include carbon dioxide and methane, CH4, and asymmetrical polar molecules include HCl, NH3, and water. Those are the exact ones they listed on that question. So here you go. This is the list. You don't even have to look at my slideshow. It's right here on the core curriculum. So like I said in the earlier video, this core curriculum is the hack that breaks this whole test open. So you should really, really use it. I would have it next to me I would have it open while I'm doing questions to see if I can find the answer right on this list of things I'm supposed to know. Oops, I think I closed our Regents exam. All right, we are moving to question 9. Nope, we were on question 9. We're going to move to question 11. Based on table S. So table S has listed on it all of the 3 major periodic trends. They don't have the actual pattern. So there's a pattern to the way that the atoms change in electronegativity, ionization energy, and radius. So if you don't know what those 3 things are, that's a problem. So those are your 3 definitions you must know for periodic trends. That's electronegativity. Again, it'll be in the slideshow. Ionization energy, I'm just going to abbreviate, and radius. Those are the 3 trends. And then there's a little blurb about ionic radius because you'd have to talk about that too. So in this case, you don't need to know the pattern because they're asking for a specific element. And they're basically saying you could just look up the number on table S, but you have to know what you're looking for because they didn't tell you which of the 3 things you're looking for. So if I go to the reference table and I go to table S, which is all the way at the end after the periodic table, okay, they have on here all 3 trends: ionization energy, electronegativity, and atomic radius. But they didn't tell you which one you're looking for. They gave it to you in kind of a vague way. So the one you're looking for represents the attraction for electrons in a chemical bond. That's a working definition of electronegativity. So you have to know this definition. It's really critical. It's also really easy. Once you remember this definition, it's an easy point on the test. So all you're going to do is go on table S and look for the person who has the greatest electronegativity. Now, if you memorized your trends, you don't need table S because now you're dealing with a question that's going to take you too long because you're going to have to look at a bunch of numbers by element. If you know the trend for electronegativity, the trend for electronegativity is that fluorine has the highest electronegativity. He's the best at taking electrons from people. Every time you're headed towards him, whether you're going left to right or whether you're going up from the bottom, up a group, if you're headed towards fluorine, you're going up a group or you're going this way across a period. Remember, these rows are called periods. Then your electronegativity is increasing. If you're moving away from fluorine, then your electronegativity is decreasing. So essentially, if unless it's confusing, like they give you elements that are all too close, like if they gave you chlorine and oxygen on this list, I might look up those two numbers just to make sure I know which one's higher. But they didn't give you chlorine and oxygen on this list. They gave you uh, oxygen, sulfur, selenium, and tellurium. So who's closest to fluorine on this list? Probably oxygen and sulfur. But since oxygen's right next door to fluorine, I'm going to take a stab that it's oxygen. He's also the highest in the group, which would make his electronegativity the greatest. So this allows me, knowing the trends allows me to knock it down to just two of these. So if I really want to go back and look it up on table S, I only have to look up sulfur and oxygen. And I'm not going to look up selenium and tellurium because they're just too far away from fluorine to be candidates. All right, so I'm going to say the answer is oxygen. All right, number 33. Now, this is again where the first section of multiple choice questions ends here. I am now in the second section of multiple choice questions. And at the beginning of the second section, we often return back to atomic theory again, but the questions are a little more involved. Oh, I guess we should have done 31 in here too. Hmm. I probably put it under nuclear because that has to do with isotopes. All right, 33 and 34. So 33 is what's the number of valence electrons in an atom with a ground state with an electron configuration of 2, 8, 18, and 3. You don't have to look this up on the periodic table. They gave you the electron configuration. Um, so all you really needed to know is that the valence electrons are the outermost shell of electrons, and they are the last number in the electron configuration. So the answer is 3. This is like such an easy point if you know what you're doing. All right, now 34. I'm really tempted to loop back for 31 because I feel like I should have put it with this topic. Which statement describes the general trend? So this again, you need to know your general trends. There are three of them: electronegativity, atomic radius, and ionization energy. In terms of fluency of remembering those trends, there is a pattern to them. And that is that electronegativity and ionization energy have the same pattern on the table, and atomic radius has the opposite pattern, which means as electronegativity is going up, ionization energy is increasing. Make sure you know the definition of ionization energy, and that atomic radius is decreasing because they're doing opposite things. This is a fluency plan, right? What's my fluency plan for remembering the periodic trends? One, I have to make sure I know the definitions. Two, I have to sit there and look for something that helps my brain hold on to this. Is there a pattern? Is there a trick? Is there an acronym? Am I going to draw it out on the table until I get it? Do I understand why the electronegativity is increasing as I go towards fluorine? There's got to be something for you to hold on to or you're not going to be able to remember it. All right. Um, so the general trend in electronegativity is that it increases as you go towards fluorine, and atomic radius is the opposite trend. So that's going to be decreasing as you go. Now they're bringing up period 3 in order of atomic number. So I'm going to pull up the periodic table. I would take out my periodic table and just look because I need to know what direction I'm heading in. Don't let all of the extra language they use in the question confuse you, though. I'm in period 3. Period 3 is marked right here for you. Period 3 is a row that goes all the way across. Okay. They're saying I'm going in order of atomic number increasing. This is their favorite way of making it more confusing instead of just saying go left to right. They say in order of atomic number. The elements are always increasing in atomic number. They increase one at a time. They're in order on the periodic table that way. So 11, 12, 13, 14, I'm going left to right. So I am headed toward fluorine. If I'm headed toward fluorine, what's happening is my electronegativity is increasing and my radius is the opposite. So if my electronegativity is increasing, my radius is decreasing. Now I just have to go back to this question and take that apart. right? And of course, it's one of these stupid multiple choice questions where everything is too long. So notice that I did this in this order. First, I recalled my knowledge without looking at the multiple choice answers. And I made sure I knew what I was talking about before I let them throw me off with all these confusing answers. The second thing I'm going to do as a strategy is where the end is, and hopefully I did the strategy enough times that you're getting the hang of it. Wherever the end is, I'm going to cut these answers in half, and I'm only going to do one half. So the first thing I'm looking for is as I went across period 3 in order of increasing atomic number, I realized I'm moving towards fluorine, which means my electronegativity should be going up. So that eliminates, based off the first half of the answer, these two choices. That leaves me with two more choices where electronegativity is increasing. Now I just have to talk about the atomic radius. Now, what I said was atomic radius is the one trend that's the opposite of the other trends. As people get more electronegative, they're good at holding on to their electrons, so they tend to pull them in tight to themselves. So, what's making them look bigger or smaller isn't how many electrons they have, so much as how much are they pulling them in. Okay, and that's especially if you're staying in one period, because as you go down to the next period, people do actually pick up another level of electrons. They pick up another energy level, which is, of course, going to make them a little bit bigger, which is why atomic radius also increases as you go down a group, um, because people pick up more shells of electrons, so they get a little bigger. So atomic radius should be uh, decreasing as electronegativity increases because they're opposite trends. So that's that one. So I addressed it in two sections. First, I said what's true about the electronegativity. That got me down to a 50-50 shot of getting it. Then I said what's true about the atomic radius. Now, if you really wanted to, if you knew you could do this question because you have table S, but you didn't remember the trends and you really wanted to sit there and break it down in numbers, I would circle this question and come back to it. And when you are finished with all the stuff you are sure about, sit there with table S and write all the numbers out and figure it out because it's still a point. And if it's the difference between you getting 49 points and 50 points and passing the test, it's worth it for you to do it. So there is a way for you to work this out using table S. It's just going to be way more time consuming than just knowing your trends off the top of your head. All right, that brings us to 38. All right, so the reason I put this one in this category is because it does have to do with your knowledge of the periodic table and also with atoms bonding. These are particle models, and you guys tend to get really confused by them. But before we even start looking at the pictures, let's talk about what element. This is one of those times actually where the element and the STP is actually relevant for a change. Um, so it is neon, and we're at standard temperature and pressure. So based on the very first slideshow on the periodic table, there's two things you should know. Neon is a noble gas. I'll pull up the reference table for a sec. So where is neon? He's right there. He's in group 18, which makes him a noble gas. And right in the name, it says that he's a gas. Okay, so very first thing we're looking for is we should not be accepting any particle diagram here that's not of a gas. So let's eliminate this stuff one at a time. The first is this is not a gas, and this is not a gas. They look a little bit like liquids to me. They're a little too sloppy to be solids, but they're definitely not gases, right? In a gas, you're going to see everybody really separated and moving around the whole container because that's how gases behave. The second thing we need to know is this single atoms or are these diatomic molecules? Okay, now one thing you could do is you know your diatomic molecules. If you know them by heart, the magic seven, it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And neon's not on that list. So he should not be represented uh, as a diatomic molecule. So that leaves that out. But the other thing you need to remember is why do these people form these little pairs? These are some really reactive elements. Oxygen, hydrogen, fluorine, they're super reactive elements. In fact, fluorine is so reactive that very few chemists in the world even actually work with that element. It's so dangerous. Um, the difference between group 17 and group 18 is huge. It's just a huge difference. Um, you've got the most reactive elements on the periodic table. I brought this up in one of the other videos, living right next door. So here's my most reactive. These are the halogens living right next door to the least reactive elements in the world. Like that they just don't want to give you the time of day. So it's kind of weird and easy for you guys to get these two groups confused. People over here are so reactive that if you leave them alone with only atoms of their own element, they insist on bonding with each other just to lower their energy level and get more comfortable. And that is why they are diatomic gases and they are never alone. But these people are just not going to do that. They don't make bonds because they don't need to. They already have 8 outermost electrons. They're very energetically stable, and that makes them inert, meaning they are non-reactive and they do not make bonds with people. Okay, so you have to remember this when you're looking at diagrams like this. Um, Neon will not be a diatomic molecule. Neon atoms do not like to bond with other people. They will all be alone. So the answer is choice 1. All right, that was 38. Let's go over. All right, we are going to 54 now, which means we are officially in the part 2s. This is a big grouping of questions, and they are a little bit about the stuff on the periodic table with the trends and atomic radius explained, and a little bit about just your general knowledge of the periodic table. Okay, so these are fluency tasks, most of them. Some of them are understanding tasks. So they're talking about beryllium, magnesium, calcium, strontium, and barium. Now, they don't actually make you even figure out where these people are. They tell you that they're in group 2 on the periodic table. So where am I on the periodic table right now? I'm in group 2. This is a group. This way is a period. Okay, so rows across are periods, up and down is a group. Everybody in the same group has the same chemical properties, meaning they make bonds the same way. That's because they all have the same number of valence electrons. And you need to know the names of the major groups. If you don't know the names of the major groups at this point in the game, that's a serious fluency problem. Okay, so however you decide you're going to do the fluency for this, whether you're going to sit down with a table you print at home and color it in, um, you need to make sure you know your elements, right? So let's run through them really quickly because it drives me nuts that you guys don't know them. Group 1 are the alkali metals. These are the most reactive metals on the periodic table. They are never found alone in nature, meaning you cannot like mine sodium out of the ground like you can with gold because it's so reactive that it will always, always be bonded to somebody else. Please don't forget that hydrogen is not included. It's placed over here for this is a little higher level chemistry than we want to talk about, but it is generally it's classified as a non-metal and it's a gas. Well, these guys are all metals that are solids. Group 2 are not the alkali metals. They have a different name and you cannot confuse them. Okay, if you go on the test for this part 2 question and you write alkali metals, you're wrong. These are the earth alkali metals. Okay, they are also just metals. So depending on how they ask the question, you don't have to tell them which type of group it is. This whole section of the periodic table, everything from the staircase over, sorry, I'm actually drawing the staircase wrong. I forget that on this table they don't have it marked. All right, so where this line is generally speaking where they mark where the metalloids are, but their marking is obnoxious, right? This is boron and silicon are metalloids, but then the pattern is that it goes like this on the staircase. So actually, germanium and antimony are also metalloids. Now, typically, polonium and astatine are not included. Sometimes they are on some tables. Polonium is radioactive, and acetine is literally one of the rarest elements on the planet. So I think we're a little on the fence about making them metalloids. I suppose polonium could be a metalloid, but it's sort of more important that it's radioactive. So you're generally going to find that some tables don't include it. So everybody here, aluminum, gallium, tin, bismuth, lead, everybody's underneath that staircase. These guys are all metals. Everybody over here, 2/3 of the table, they're just all metals. Okay. Your non-metals are after that. And no, they're not all gases. I don't know why you guys get this stuck in your head. All non-metals are not gases. So when you review the periodic table slideshow, you need to look, there is a list. Okay. Carbon is not a gas. We just spent a lot of time talking about carbon as an allotrope. Do you think diamonds are gases? Get that out of your head right now. A lot of them are gases, but not all of them. Carbon, phosphorus, sulfur, selenium, are all solids. Iodine is technically a solid at STP, and bromine is technically a liquid at STP. So yes, there are a lot of gases over here, but just because it's a nonmetal doesn't mean it's a gas. So there are both solids and liquids. Sorry, there's all three are there. There's solids, liquids, and gases in the nonmetals. So if you don't go back and review the slideshow, I'm telling you right now that that's true. All right, let's go back to the full line of questions. So based on the location of the group 2 elements, state the element classification. So that's your key word, and you only have to state it. Don't explain it. Don't spend time writing me 2 sentences about where they are on the periodic table, and that makes them a metal. It says state. Then what am I supposed to be stating? Element classification. If you really guys have to really get this down. Classification means a category you put it in. What are the 3 categories of elements? Metals, nonmetals, metalloids. So you could literally just write metals for this and you're good. Now, if you decided to write earth alkali metals, which are the group 2 metals, you'll get it right. If you can't tell the difference between an alkali metal and an earth alkali metal, though, and you write alkali metals, you're going to get it wrong. So this is one of those cases where writing too much could get you in trouble. So just put metals because that was a completely acceptable answer. Explain in terms of electron shells why the atomic radius of calcium is greater than the atomic radius of magnesium. We're still in the same group. Atomic radius is essentially the distance from the nucleus to the outermost electron, which is shown on the periodic table as the valence electron. It's the last electron in the configuration. So again, I'm staying in group 2. And the 2 atoms I'm comparing to each other are magnesium and calcium. So if you look at their electron configurations, magnesium has 1, 2, 3 energy levels, and calcium has 4 energy levels. And that's all there is to it. Calcium will have a slightly larger radius than magnesium. And if you look up their radius, you can actually also look it up and make sure you understand that calcium is bigger. If you know the trend, atomic radius increases as you go down a group, and the reason is because as you go down a group, people pick up more electron shells. It's not the same, the trend is not the same if you go across a period, because if you notice, everybody has the same number of shells, and so that's not going to change, so that's not determining what their radius is. All right, so how do I answer this question? Again, this is explain. I said in the part 2 review, explain does not mean you need to come up with your original explanation. You are not an atomic theorist. You're not a physicist that deals with atomic structure. They don't expect you to have your own original explanation. What they want you to do is either reiterate to them, repeat a definition or a known model that you understand from your time in chemistry that explains. They're telling you also why the atomic radius of calcium is greater than magnesium. They already told you calcium is bigger than magnesium. So don't talk about that in your answer because they told you that. What they want to know is what comes after this wonderful phrase in terms of. They want to know in terms of electron shells. So what do you need to talk about in your answer? Electron shells. Okay, in terms of electron shells, why is it bigger? And you just have to say, Calcium has four electron shells, and magnesium has only three electron shells. And you're done. That's the whole answer to the question. Because you brought up the electron shells, the number of electron shells, you answered the question. That's all you need to do. If you were to just write, well, calcium is larger than magnesium, you're wrong. And you also repeated something they already said in the question. So you're just gonna piss off the person who's scoring your exam. All right, the general trend in first ionization energy for group two, you need to state it. Okay, so as you are increasing in atomic number. So let's go back to the reference table again, zoom in on group two. Here are the atomic numbers 4, 12, 20, 38. So increasing means I'm going down the group. If I know my trends, I should know electronegativity is going down here because I'm moving away from fluorine, I'm going down. And ionization energy has the same trend as electronegativity. So ionization energy will be decreasing. And again, you don't have to get fancy with it. Let's just look one more time at the language. They just said state the general trend in first ionization energy. Again, this is one, if you didn't memorize your trends, you could get the point for this if you sat down with table S and wrote down the ionization energies off table S and then just looked at the pattern. Is it going up or is it going down? That would be maybe more time consuming. So this might be one you want to circle and come back for. But the general trend in first ionization energy as you go down a group is that it's decreasing. And since it says state, you don't have to rewrite the question or anything. You just have to say decreasing. If you are nervous about doing that, you could say the first ionization energy decreases as you go down a group, and that would be great. Especially since they're asking you for a pattern, it's always good to give them the full pattern. The low risk way of knowing you're not going to get the question wrong. All right, we are now going to 62. All right, this is under bonding because it has intermolecular forces in it. So this is going to be a little bit of a long explanation. This is why I am indexing the questions for you so that if you're doing the practice, you can just look at which topics I'm reviewing on the slideshow. I'll tell you which exam I'm on, and then you can go only to the questions that you want somebody to explain to you. All right, so intermolecular forces, we really got to talk about this. A molecule is a group of atoms that are covalently bonded to each other and they are nonmetals. Okay, this doesn't apply to ionic compounds at all. So no salts. Potassium chloride does not do this. Only molecular substances do this. So we're talking things like water, alcohol, ammonia, things that have only nonmetals bonded together to make molecules. Molecules are groups of atoms like what I just drew. Water. Okay, molecules are groups of non-metal atoms that are clumped together. So what you need to understand is the difference between an intermolecular force and an intramolecular force. Now, they don't bring up the second term in most cases. Intra means inside, and inter means in between. Okay. Intramolecular bonding is what's holding the molecule together. Like what's making this hydrogen. This is water, by the way, you guys. I'm sorry. You should know what water looks like at this point. This is an oxygen, and these little blue ones are hydrogens. So this is two hydrogens, 1, 2, and one oxygen. Okay. What's holding this molecule together? Intra means inside. I just said is a covalent bond between two non-metals. Right? So what's holding this molecule together is an intramolecular bond. That's covalent bonding. That's not what I'm talking about here. What I want to know is in a container of water, why do a bunch of water molecules hang out together? Why do they do that? Why are they liquid? Why do they stay together? Why don't they just be gas and go float away? I mean, they do that sometimes. It's when they form water vapor, but they don't do it a lot of time. Like a lot of water in the world is currently in its liquid state. like 2/3 of the planet is covered in oceans, right? Water tends to like to be a liquid. Why? Why do water molecules like to stick to each other? This is an intermolecular force. Okay. Intermolecular forces are forces that are between molecules. So I'm going to draw another water molecule here. Oh, I should have done this on paint, so I could have just copied it and it takes so much time. Sorry, guys. All right. If I draw another water molecule, what I want to know is why does this water molecule want to hang out with the other one? There must be a force between them that makes them attracted to each other. So forces between molecules are what, on a larger scale, are often what's holding a lot of liquids and solids together. So particularly water, and particularly you. You are mostly made of, or oh, is there? Oh, sorry, my dog just came to get me because there's thunder. Um, particularly intermolecular forces between water molecules. This is a type of intermolecular force between polar molecules. Polar molecules are molecules that have uneven charge distribution, like we talked about before. That uneven charge distribution is that electrons are tending to hang out with oxygen. And so they get a kind of a partial charge. This is not a real charge. This is not ionic. But it's enough of a charge to make these guys want to hang out with each other. This positive end, where the hydrogens are, is going to get attracted to the negative end of the molecule, which is where the oxygen is. Okay, they sometimes make you draw this on a Regents, so you should really review it. I have a lot of pictures of it in my intermolecular slideshows. Okay, so this is important because this was a lot of, hold on, I'll go back. This was a lot of very specific knowledge, but it's still memorizable at this point. You can memorize kind of a shortened version. The issue is if you're memorizing without too much understanding, you're probably not going to be able to avoid the traps they put in these questions. So it is more important that you understand it. So explain in terms of intermolecular forces. That's what I have to talk about. Why the boiling point of a molecular substance is lower than the boiling point of water at standard pressure. This is actually something we talked about from the very beginning of the year. And that is what makes things have certain physical properties is because of how attracted its particles are to each other. So you've known from the very beginning of the year that if something is a liquid, it has very strong attractive forces. And if something is a gas, it has weak attractive forces. So if it's hard to get something to boil, it's because I have to overcome all of the forces between the molecules before I can get it to go to a gas. All of those forces have to be overcome. Um, so in terms of intermolecular forces, the boiling point of a compound that's lower means it will have weaker intermolecular forces holding it together. So I have to look and see which slideshow I have this in, but I can give you a slideshow from Q1 that has this in it because intermolecular forces is a really fancy word for just whether or not particles are attracted to each other and how attracted they are to each other. All right, so that does fall under bonding, but I think we can handle it in a simpler way if we want. All right, 66. The table below shows 3 compounds useful for medical purposes. This is calcium sulfate, magnesium hydroxide, and zinc oxide. Identify 2 types of bonding in the compounds used to make plaster casts. Okay, this is a pat answer, meaning there's kind of only one option. If you've got a polyatomic ion, you've got 2 types of bonding going on. You've got a calcium with a +2 bonded to a sulfate. Sulfate is a polyatomic ion. Polyatomics is a very bad Lewis structure. I'm just going to warn you now. Sulfate is a polyatomic. Polyatomics are weird little animals because they are held together with covalent bonds, but they, as a group, are a charged ion. So there's covalent bonding inside here, and then there's an ionic bond between these two people because they have opposite charges, and that's how they're hanging on to each other. So because this little cluster, this little grouping, acts like a family with a charge as an ion, this is ionic bonding here. But inside the polyatomic itself, there is covalent bonding. Okay, another hint to you, aside from metallic bonding, is that there are really only two broad uh, categories of bonding for compounds. You're looking at a compound where you've got atoms of different elements combining to form a new chemical. There's only ionic and covalent bonding. So if you just listed the two types of bonding you most commonly know, you would get it right. The only trap you could fall into is accidentally bringing up metallic bonding, which doesn't apply here because metallic bonding is, you'd have to have a pure metal. And there's nobody on this list that's just a metal by themselves. These are all compounds. They say that in the question. Okay. Metallic bonding, there's no such thing as a compound in metallic bonding. There's alloys, but they're a little different. We don't really get into alloys much in Gen Chem. Maybe we should. I don't really know that I need to add anything else to confuse you. 67. Identify a noble gas that has atoms in the ground state with the same electron configuration as a positive ion in magnesium hydroxide. Okay, I think I went over this in the slideshow with valence electrons that I'm going to attach to this, but I'm going to go over it really quickly here. All right, identify, so the number 67, the noble gas that is in, all right, so magnesium can only pick up one charge, which you guys probably know. It's also what's listed on the reference table on the periodic table under oxidation states is +2 is the only charge possible for a group 2 ion. Okay, if you were to look at the periodic table though, with this in mind, right? So here's our magnesium with a +2. How does he get this +2 charge? He loses electrons. All right, so when you pick up a charge or when you make a bond, either by sharing your electrons, that's a covalent bond, or by giving or taking electrons, that's an ionic bond. The goal is the same. The goal is to get eight outermost electrons. And so you're just going to accomplish that in different ways. For an atom like magnesium, it's very convenient for him. I'm very sexist today. I need all my elements boys. All right, let's be magnesium girl today. What's convenient for her is she needs this to be her outermost electron shell. She needs 8. Picking up 6 extra electrons from somebody else would take like really a lot of energy. Pretty much no one can do that, not even fluorine. Not even, big, very electronegative non-metals can do that. For the most part, the most that they pick up tends to be about 3. So that just takes too much energy. So the best thing to do in terms of doing this and conserving, doing it with the amount of energy that you have would be like, well, why don't I just get rid of these electrons and then I'll have 8 in my outermost level. This is why you pick up a +2 charge. You get a positive charge when you give electrons away. I'm not going to go over it in a lot of detail. But just know, plus means you lost, minus means you gained. The number of electrons you lost or gained, that's the charge, that's the total charge. So +2 means you lost 2 electrons. You gave them up to somebody on purpose because it was more beneficial for you. You now get to have a very stable electron configuration with 8 electrons in your outermost level. So now all you have to do after you look at that situation is go over to the noble gases and see who has that electron configuration 2-8. Who has the electron configuration 2-8? Should be neon, yeah. And there it is. Electron configuration 2-8. It's neon. Right? So it's actually a pretty easy question, but it is a lot of back and forth, and you do have to know that this is what they do when they bond. So the answer to number 67 is just neon. Because this question says identify, you don't have to explain, you don't have to write a sentence, you don't have to say anything else. You just have to say it's neon. And if you want, you can just say Ne. Just make sure you don't put N, because if you put N, it's nitrogen and it's wrong. So I almost would rather you just write out the name of the element. It's neon. All right, based on table S, determine the electronegativity difference for the bond between zinc and oxygen. This should be a super easy question. You're going to go on table S. You're going to look up the electronegativity. You should know from a basic math class that the word difference means subtract. And you're going to look it up for zinc and for oxygen. So we're back to the reference table again. We're going to head over to table S. Yes, these questions are very involved. I'm gathering you guys have probably picked that up by now. We're doing zinc and oxygen. So the electronegativity of oxygen is 3.4, and the electronegativity of zinc is a little further down. Zinc is number 30, is 1.7. So I'm literally just going to do (3.4) minus 1.7. And it says determine, so I don't even have to show them this math. I just have to type it into my calculator. Please type it into your calculator. Type it into your calculator. Type it into your calculator. I cannot tell you how many times I have had a student not subtract these two numbers correctly and get a question wrong, even though they were doing the question correctly. You're under a lot of stress. I know you guys have done a lot of Montessori training and stuff um, to not use calculators and do your math by hand. But the last thing you want to do is lose a point on a subtraction mistake. That's just silly, right? So I do 3.4 minus 1.7. I get 1.7 as my answer. And I go ahead and write 1.7. You only have to say 1.7. You can do the math somewhere else in the booklet. It's not counted as work. So that's why it says determine. If it had said show a numerical setup, then you would have to show me that you subtracted. But you don't have to do that. All right, was that number 68? That was number 68. Yay, we're done with this topic. Okay, so hopefully those explanations helped you. I'm going to go index all the questions now so that you can jump around. You don't have to listen to me explain every single thing. And I will link all the slideshows that I think apply to this review to this description. All right, thanks so much, you guys.